All right, partial derivatives here. Don't be overwhelmed with all this new notation. We're going back to Calculus 1, in which we're doing derivatives for this chapter, for much of this chapter. And the difference is, notice we have multivariable functions, right? And we're doing multivariable calculus. We now don't just have functions of x, we might have y's, we might have z's, or any number of variables, but typically we'll see 2 to 3. So this first thing here, that weird kind of, it's a D, but it's not quite cursive. Weird swirly D, whatever you want to call that D. But just like derivative, right? If I said df or df over dx, then I'm saying take the derivative of f with respect to x. And the reason we use this different looking d here is there are more than one variable, so this is telling us we are taking a partial derivative of the function with respect to x or y. Just like a second derivative, we put a squared on the d and the x. Same thing here. Okay, it's a second partial of this function with respect to x, and the next one, second partial with respect to y. And these last two, almost always you'll get the same result, so really it doesn't matter. But the second one goes first, and we'll look at y here in a second. But so we're doing the second partial of a function, but first we're going to look at y as the variable and treat x as a constant. And then we look at after we get a result, we'll do the partial with respect to x. Okay, so this outer one, the one furthest to the right, is what we do the derivative with respect to first. All right, so I have 3 examples here. The first one, we're going to go ahead and do them all to explain exactly how these work and how second partials work. The next 2 we'll just do partial x, partial y. Okay, so if we look at this first example, the function is 5xy. Partial f partial x tells me that x is the variable. Treat y like it's a constant, right? Pi, right? When we add pi, we treat that as a constant as well, even though pi technically, right, is a number, 3.14. It's an irrational number. Why? We have no idea here. It is a variable, but when we're doing a partial, we treat it as if it's not. So if x is the only variable here, the derivative of x is 1. So therefore, the partial of the whole thing, we just get 5y because the x, right, think of that as the variable, 5y is a constant. Hopefully that makes sense. If we look at partial y, okay, now probably should have switched colors, that's all right. Y is the variable, and the way it's written here, I think this makes a little bit more sense, right? 5x is constant. So our derivative is 5x because y is the only variable, and the derivative of a variable, to the first degree is just 1. Alrighty. Now, let's go ahead and do the second partial. I'm going to do it right below here because this says I need the partial of x, right, which we have, and then I'm going to use this result to get this result. Okay, so I'm looking now at 5y as my result, and I'm taking the partial with respect to x of that. Well, there is no x. 5y is a constant, so if I'm talking about a partial with respect to x, that answer is 0. For the next one, very similar, right? Second partial with respect to y, there is no y here, so that result is 0. Now, if we do second partial of, I'm going to do the last one that I've written over there first, right here. And the reason is, remember, this one says I need to take the partial with respect to x first, which is the 5y. Now I look at 5y, and I'm doing the partial with respect to y. Well, the derivative of 5y with respect to y is 5. Now, really quick, I said I'd explain why it's written like this. It's because it's just a short way of saying this. Okay, not really multiply, but it's a composition, really, right? If I said to do this first, and then I'm going to take the partial with respect to y after that. Well, combining them, you can almost look at it like, and why I even put the dot there, it looks like multiply, right? Partial y, partial x, partial y, partial x here. So we actually do this right-hand one first, and then we do the left-hand one. So therefore, in this example, partial squared, we did the y first. So next we're going to take that result and do it with respect to x. So when we did y, we got 5x. So the second partial now with respect to x is 5. And to add, like I said, almost always, there are certain times that you won't see them in this class. There are certain functions, weird ones, that you don't get the same result. But if you do x first then y, or y first and then x, in this course, you will always get the same result. Cool. So that's, a very basic function there, but that's the idea. That's how these partial derivatives work. So let's look at this next one. It gets a bit more complex. When we do derivatives, and integrals for that matter, often we rewrite them first, right? That is the first step. So y in the denominator, we think of it as -1 power. X in the denominator, we think of it as the -1 power, right? X to the -1. So now let's do partials. We'll do partial with respect to x. Okay, so x is the variable. The derivative of x is 1, so therefore I just get y to the -1. X is the variable, y is a constant. So the derivative of x to the -1 is -x, and then we subtract 1, right, to the -2. And we still had that y there. Right, that is a constant, it doesn't go away. Think of it, if we were doing derivative of 5, right, it would be -5, here's the 5, x to the -2. Now that's an ugly answer, so typically, let's rewrite that, minus y over x squared. That looks much better. There is your partial with respect to x. Partial f partial x is one way to read that. So now partial f partial y. Okay, let's go back to f up here. Y is the variable, so we get -1, and then x stays, right? Y to the -2, we subtract 1. Again, y is a variable, so derivative of y is 1, so we just get x to the -1. Rewrite that to clean it up, -x over y squared plus 1 over x. I'm not going to worry about getting an LCD and combining them. I think that looks just fine the way it is. Great. Last example. Again, a square root. We want to rewrite that to the 1/2 power. Remember, anytime you have something in parentheses or square root and you go to do derivative, you have to remember chain rule. Let's stay consistent here. Partial f, partial x. All right, x is the variable here. Well, this requires chain rule. So Remember, you treat this entire thing like it's the variable. We bring down the 1/2, leave all that inside stuff alone, subtract 1, and then multiply by derivative of the inside, which is only 2x when we're talking partial f partial x. Because remember, y is just some number, it's some constant. That derivative is 0. So the derivative is 2x. Let's clean this up a little. 1/2 of 2, right, those cancel. So now we just have an x in the numerator, and this x squared plus y squared to the negative 1/2 becomes x squared plus y squared square rooted in the denominator. There's partial f partial x. Once you get the hang of these, we'll start to go pretty quick here. This one's going to be very similar, it's just now y is the variable, right? So we still bring down the 1/2. I still subtract 1. But now when I do chain rule derivative of the inside, y is the variable, x is a constant. We can reduce the same, and therefore this result, like you said, would be very similar. It's just we have y in the numerator instead of x. Alrighty, hope this helps with notation especially, but kind of the process behind partials. Once you're, proficient at derivatives, partial derivatives really aren't bad at all.